everyone. Can you hear me? Can you see me all right? Please give me a thumbs up before we start so I can know that you can hear me and you can see me. How's everybody doing? Are you guys feeling good? First week is going well, I hope, for everyone. Awesome. Okay, so let's get started in this Wednesday evening lecture. Thanks for joining. So we're going to be talking about mathematical reasoning and proofs in this lecture. This is kind of like part 2 of the introduction to the course. There are a couple of reasons, I want to give this lecture right now. Well, one reason is that, this course is about, mathematically reasoning about computation, and you will be writing a lot of proofs in this course. And we want you to improve your skill in terms of writing proofs and reasoning mathematically. So let's agree on what do we mean by mathematical reasoning? What do we mean by mathematical proof? In the context of 251, but as well as, in a broader context in mathematics in general. And the second thing is basically, in the first lecture, I already mentioned a little bit the connection between computer science, the birth of computer science, and mathematics and the foundations of mathematics. And in particular, the quest to formalize mathematics and mathematical reasoning was precisely the thing that led to the birth of computer science. So, I want to explore this a little bit more now, maybe from the mathematical side of things. The first lecture, in some sense, theoretical computer science is in the intersection of computer science and mathematics. The first lecture was sort of an intro from the computer science perspective, if you will. And now this will be another intro from the mathematics side of things. Okay, so in the first lecture, we started with the questions, what is computer science? What is theoretical computer science? And that was the main focus for that lecture. And now we're going to be asking what is mathematical reasoning and what is a proof. Okay, and I want to actually start with asking you, giving you some example proofs and ask you whether you think these are legit proofs or not. Okay, so first proposition is start with any number. If the number is even, divided by 2. If it's odd, multiply it by 3 and add 1. If you repeat this process, it will lead you to the sequence 421. And once it's 421, then it will repeat 421, 421, 421. And the proposition is that if you start with any number, you will end up always with 421. And here's the proof. Many people have tried this. No one came up with a counterexample. Okay, so is this a valid mathematical proof? Do we accept this as a proof? No, I'm seeing lots of no's. You are right. So in mathematics, we have higher standards for proofs. But it is actually interesting to note that in many other, sciences, the notion of proof is kind of similar to something like this, actually, right? But you're correct that in math, our standards are a bit higher. And in fact, this is not a proposition. This is known as Collat's conjecture, a very important open problem in mathematics, a very hard one. Okay, next proposition. 313 times x cubed plus y cubed equals z cubed has no solution for x, y, z and the positive integers. And the proof is the following. With a computer, we verified that there's no solution for numbers with at most 500 digits. Okay? All right, so wait a minute. So you say no, but 500-digit number is a huge number. If I wanted to express the number of particles in the observable universe, I would need about 80 digits to represent that number. Now we're talking about 500-digit numbers. These are so big, I cannot describe to you how big. So if there's no counterexample up to 500 digits, there's no counterexample, right? Well, turns out, you guys are saying no, yuck, and things like that. Turns out this is not even true, right? So actually there is a counterexample with about 1,000 digits or something. And it's kind of crazy, right? If you think about it, it's very counterintuitive why the smallest counterexample to this would be that big. But it turns out it is. And so you have to be careful in math, right? So intuitions are not always correct. And yeah, proof by example doesn't work. You have to be sure. All right, here's another proposition. Given a solid ball in 3D space, there's no way to decompose it into a finite number of disjoint subsets, which can be put together to form two identical copies of the original ball. So what this is saying is that there's no way to take a ball in 3D space, okay, partition it into finite number of pieces, and then put those pieces back together in a way such that you create two copies of the original ball. Like there's no way to do that, is what the statement is. And the proof is obvious, right? So obviously you can't do that, right? Is this obvious? Well, turns out this is actually possible. This is the famous Banach-Tarski theorem, sometimes called a paradox because it's so counterintuitive. But yeah, it is possible to do this, right? So the proof uses group theory. Pieces are weird scatterings of points, no meaningful volume. So here really, like, your intuition about physical space is wrong when it comes to this kind of thing. Like when this theorem says 3D space, what it means by 3D space is not physical space. This is like really R cubed we're talking about, like the real numbers cubed, and that doesn't behave like physical space. So you have to be careful. All right, so then, given the previous example, if I said, 1 + 1 = 2 and the proof is obvious, like, is it obvious or not? You might be worried now about what we can consider to be obvious and what we cannot consider to be obvious. But, this is okay. This is actually indeed obvious. Don't worry about this. Let me give you another example. This is the story of the four-color theorem. Okay, so the four-color theorem is a conjecture from 1852, and the statement is the following. It says, any two-dimensional map of regions can be colored with four colors such that no two adjacent regions get the same color. So you can imagine, let's say you have some kind of a map. It could be like the United States map, or it could be some other arbitrary shapes. And it says that you can always color such a map with four colors such that if there are two regions that are, sharing a border, they will not have the same color. Or in other words, if there are two regions with the same color, they should not be sharing a border. Okay, so that's the statement, that you can do this for any two-dimensional map. So what happened with this conjecture? So let's look at the timeline here. 1879 now we are at, and it was proved by Kempe, American Journal of Mathematics. Okay, and so that's good. We have a proof. And a year later, an alternate proof was given by Tate. And so now we have two proofs, so that's very good. Now, 10 years later, Haywood finds a bug in Kempe's proof. So that's a problem, but okay, at least we have Tate's proof, so it's okay. But 1 year later, Peterson finds a bug in Tate's proof. So now we're back to conjecture, like it was a theorem, but now it's a conjecture. So then look at the timeline. Nothing happens for a long time. Until 1969, Heesh showed the statement could in principle be reduced to checking a large number of cases, about 2,000 cases or so. So that's a big number of cases. Who's going to check those cases? But this is an interesting time in history, right? 1969. So what do you think people did to check these cases? What can we do? Computers, exactly, right? So 1976, Apple and Hacken wrote massive amounts of code to compute and check about 2,000 cases, which took about 1,200 hours of compute time. Okay, so now, much controversy at the time. Is this a proof? So now I want to ask you this question. Let me know now in the chat. What do you think? Do you accept this as a proof? If no, why not? So what might be I'm seeing a lot of yeses in the chat. What might be some arguments against it though? Computers can have bugs, right? So that's true, right? What if there's a bug? It could be a physical bug. There could be a bug. I mean, there could be two kinds of bugs, right? There could be a bug in the software. There could be a bug in the hardware. There could be a bug in the compiler. But, a good counterpoint, humans can have bugs as well, right? We make mistakes. What if they didn't capture all cases? That's a good point. If humans cannot understand the proof, then can it be considered meaningful? Very good point. Yes, I mean, that's one of the things that I was looking for. It doesn't seem like we're gaining any deep insight about why the theorem is true, perhaps, and is that okay? Let me summarize some of the objections you raised up, right? So arguments against this is maybe there's a bug in the code, as you guys pointed out. Maybe there's a bug in the compiler. Maybe there's a bug in the hardware. But the thing is, you can say these kinds of things for a normal human proofs that are checked by other humans, right? So we miss bugs in proofs all the time. There's a funny story. There's one of the most prestigious mathematic journal, that's actually the top math journal in the world, has 2 papers published, accepted and published, one proving X, the other proving the negation of X. Okay, so this happens. We have to be careful about that. So that's one thing. But I think maybe the most interesting objection might be that there is no insight derived from this kind of an argument. And this now brings up a very interesting question. Is that actually a requirement, or should that be a requirement for a proof, right? And this is interesting because I would say kind of yes and kind of no. Like, I can make arguments for both sides. For one, why do we prove stuff? Sure, an element of proving stuff is to know whether something is true or not, but that's not the only reason really why we prove stuff. We prove stuff because we want to understand why, if something is true, why it's true. If it's false, why it is false, right? So that's one perspective. But on the other hand, what does it mean to really gain insight or understand the proof, right? I mean, if you wanted to formalize or make precise what you mean by proof, you can't really make that dependent on something very subjective, like you gain insight. You will not be able to make that precise. To finish this story off, there are simpler computer proofs now from 97, for example, Robertson, Sanders, Seymour, Thomas. And now this is definitely an established theorem in this sense. And one other thing I can say is we computer scientists actually have developed interesting notions, extending the notion of proof in interesting ways. And one of the ways we have extended the notion of proof is by defining this thing called zero-knowledge proof. Okay, you might have heard about this, but basically a zero-knowledge proof is a proof such that, it gives no information about the proof other than the one bit of information, which is whether the theorem is true or false. Okay, so it's just in that sense zero knowledge. It just gives you one bit of information and no information other than whether it's true or not. And this can be useful, right? If I prove the Riemann hypothesis or the P versus NP question, and I want to convince you that I have a correct proof of this, but maybe I don't trust you because if I share the proof with you, you might go and collect the $1 million prize for yourself. You might steal the proof. So is there a way for me to prove this to you, prove that I have a correct proof without revealing anything about the proof to you whatsoever? And it turns out it is possible. It's kind of amazing, very counterintuitive, but it is possible. And that's very interesting. And this kind of thing actually has very interesting applications. Does anyone know a modern application of zero-knowledge proofs? In terms of security, it's related to security. Yes, blockchains. Yeah, cryptocurrencies, blockchains, this stuff is being used. Okay, zero-knowledge proofs. It's very interesting stuff. Okay, so now, all of these examples raise a good question, right? What is mathematical reasoning? What is a proof? How can we understand it? How can we formalize it? So what I want to tell you now is let's understand good old regular mathematics. And I'm going to call this GORM. And this basically represents the kind of mathematics that, we have been doing, humans have been doing for thousands of years, right? Just the regular mathematics that we've been doing thousands of years. What is it? Well, in the first lecture, I showed you a picture of physics. It kind of looks like this, right? So you have some phenomenon that you want to understand. You create a mathematical model for it. You study it rigorously logically to create new knowledge and so on and so forth. In physics, really, the things that we're interested in understanding are really the foundational stuff, right? The fundamental properties of matter, properties of space and time and things like that would be in the territory of physics. But in general, of course, you can apply this kind of reasoning to many other things, right? So good old regular mathematics, the way I like to describe it is that it's the same picture, but it's not, just applying to fundamental particles, space, time, and things like that, but anything of interest, right? So what could it be? I don't know. Maybe you are living in the Stone Age, and people are developing some kind of an economy and exchanging goods, and they realize, okay, maybe to reason about these things we need to invent these abstract notions of numbers and arithmetic, and then use logic to derive new knowledge about numbers and arithmetic that can be hopefully then applied back to the real world, for example. It could be like people are gambling, and to understand the chance events better, they invent probability theory, right? And actually, this is precisely how probability theory was born. It was for a need to understand gambling. And then, you invent probability theory, you derive new properties, new knowledge. And hopefully in the applications, the application of this would be to make more money, right? So this is precisely how probability theory actually was born and was applied originally. It could be like, you're a farmer and you have some land, and maybe you have some weird shapes that you would like to, calculate the areas of. Maybe this forces you to invent plane geometry and, look at the applications there from that perspective, right? So a mathematician here, this is good old regular mathematics, mathematician really lives in the right-hand side of the diagram here, right? They're not too concerned with the applications or the modeling side of things, but more on the abstract world side of things. And it can be very interesting because it's sort of like you're exploring as a mathematician new intellectual territory, right? And that can be actually very magical. Like imagine, if you're an astronaut and you land on the moon or Mars and you're taking first steps of mankind, that's magical because you feel like, okay, I'm the first person actually stepping on this ground. And math is sometimes like that, where it's not like actual ground, but it's intellectual territory. And sometimes when you're doing math, you feel like, okay, I'm the first person really thinking about these things and exploring these ideas. And that can be very, very interesting. And the way you explore as a mathematician this intellectual territory is you kind of follow your gut feeling. You follow your nose. You follow what you feel is natural direction to go in without really thinking too much about applications. And I think that is the right way to do mathematics. Now, someone looking from the outside might object to that, right? So with, for example, plane geometry, a mathematician would say, okay, well, why would you restrict yourself to 2 dimensions? Let's study 3 dimensions. Let's study k dimensions, right? So it's natural to extend these results to k-dimensional spaces. Now, someone from the outside might say, why are you studying k dimensions? We live in a 3-dimensional world. You're wasting your time. You're wasting your money. But this would be the wrong perspective, right? Because you never really know what kind of applications might appear in the future. And in fact, right, hundreds of years later, maybe, Einstein comes along and says, reality is a 4-dimensional continuum, 3 dimensions of space and 1 dimension of time, right? And then years later, string theorists come along and say reality is 10 dimensions or 12 dimensions or however dimensions they have in their models. So then, you're happy that the mathematician actually, took the time to figure out k dimensions for arbitrary k, and it was very useful. So this is really how I think mathematics should progress, right? So, You don't really worry directly about applications. You follow your intuition, and whatever feels natural to explore, you go and explore it. Okay. So now I should say there's a spectrum of GORM, of course. Okay. So in terms of like how precise you are with your arguments, with your statements, can vary a lot. So on the one end of the spectrum, we can say like any kind of almost like informal reasoning with real objects even can count as a part of GORM, right? If you say something like every person is mortal, Aristotle is a person, therefore Aristotle is mortal, you're applying logical reasoning here. You're using, real world objects, but that's okay. I mean, I would count this as part of good old regular mathematics. Even though, the objects may not be, well defined mathematically. I think that's okay. Now, if you go a little bit to the middle, maybe you start reasoning with mathematical objects, like maybe geometric shapes and things like that. Maybe the stuff that you start doing in high school, writing, arguments about mathematical objects, maybe that moves you towards the middle here. And then at the other end of the spectrum, you have more formal definitions where every object that you're reasoning about has a precise definition. Your arguments are very precisely laid out. And this is the kind of thing basically that a professional mathematician would do, right? So this is a rough like spectrum of good old regular mathematics, right? You can see like there are levels or different levels to how formal you might be. Okay, but what is common to all of this is, I would say, the following, right? Mathematical reasoning in all of these cases kind of boils down to this. So you start with some truths that you assume to be true. So these are maybe like things that are obviously true. You apply some logical deductions to these truths and to derive new truths. Okay, so sort of this is the idea. And then once you have new truths, you can feed this back into the pipeline here, and you can now start with the obvious truths and then deduce truths, and then deduce new truths from those, right? So here's basically like maybe a better picture representing what's going on here. So you start with some assumed truths, which we usually call axioms. You apply your logical deduction rules to derive new truths. From there, you derive new ones and derive new ones and so on. So these red arrows, they represent the logical deductions, and these circles like are the new truths. Okay. So this is kind of the picture of mathematical reasoning in some sense, and a very nice early example that really embodies this is actually Euclid's elements, or Euclidean geometry. So 300 BC, the book Euclid's Elements, this is one of the most influential books of all time. Here in this book, Euclid gave 5 axioms for plane geometry, Euclidean geometry. You don't have to read these axioms, don't worry about it. But basically the point is that, he was very, systematic and precise about this. He said, here are the axioms, and I'm going to derive everything from the axioms systematically. And in that sense, this really set the standard for mathematics in the future, right? So like, people's understanding of mathematics was really now shaped by this, like, okay, this is really what mathematical proof should be like. And people have, been doing mathematical reasoning for, thousands of years. And, as we progress, we come up with more and more sophisticated ideas, more sophisticated arguments, more abstract concepts. And as things have progressed, we started to come to a point where things got, quite sophisticated, and some serious problems started to emerge over time. Okay, things, started to escape our intuitions a little bit. And Yeah, and then a foundational crisis began, and maybe peaked at the late 1800s, early 1900s. Okay, so let me tell you what these problems are with Gorm. So the first problem is, what is an obvious truth, right? What is an axiom? And I have a couple of different things to say about this, okay? Now, the first thing I want to say is, I'll illustrate with an example, actually. So the question here is, can we always get a satisfactory set of axioms? And let me illustrate this with an example. So here's a proof that the square root of 2 is irrational. This is the standard proof that I'm sure you have seen. You don't have to read this at all. It's not the point. But it's a proof by contradiction, basically, right? So you write square root 2 as a over b and then derive a contradiction for it. And this is the standard proof that you see in an intro proof course. Now, this proof looks legit, but if I asked you, like, would you bet $1 million that this is a correct proof? Would you bet your life that this is a correct proof that I write here? Then, you might be like, okay, stakes are very high now. So let me see, is every step here really justified or not, right? So then, that would maybe make you more focused and like really analyze this more carefully. And perhaps you can identify a step here, maybe this one, which says like, if r squared is even, then r is even. Intuitively it seems okay, but it might be something that you prove just to make sure that this is a correct proof. So then you can unwind step 4, right? And then say, okay, let me prove that if the square of a number is even, then the number is also even. And then you break up step 4 into 4a, 4b, 4c. That proves basically step 4. Okay, and this is also a proof by contradiction. And then after you do that, I can ask you again, like, now are you sure? Like, do you want to maybe look into other steps? And maybe you might be like, okay, let me look at this step 4b. So it's saying if I have an odd number, r is an odd number, then I can write it as 2t plus 1 for some number t. And you might be like, okay, well, that's maybe something that I should prove. So then you expand on that. Every number is a multiple of 2 or one more than a multiple of 2. Right, so you expand 4b to 4b1, 4b2, 4b3. And the nature of this argument is such that you define this notion of a number being good, and then you sort of apply some rule repeatedly to show that 2 is good, 3 is good, 4 is good, and so on. So now you have actually hit the axiom of induction, which I'm sure you know about, right? So the axiom of induction says, like, suppose that for every positive integer n, there's a statement s of n. Then if you know s1 is true and that for all n s of n implies of s of n plus 1, then s of n is going to be true for all n greater or equal to 1, right? Okay, good. So now this is a statement that we all agree to be true. We all agree that this should be an axiom, and we're happy about that. But now, there's a question. We did this for this particular proof, and, we unwinded some of the steps, and then we reached an axiom that we agree on. Now, the question is, if I were to take another proof of another theorem and do that unwinding, would I again hit some, axioms that we agree upon? Could there be an infinite regress? Or if I pick different proofs, would they lead to different axioms? And there's no an agreed upon set of axioms for all of mathematics, and maybe every proof leads to some other set of axioms, right? So it brings up all these kinds of questions. Can every mathematical theorem be derived from a set of agreed upon axioms? And this is actually similar. Notice that this is similar to if we were to take a Python function, you write some simple program in your Python. Well, you can unwind that and go to C code from the Python. You can unwind the C code and go to assembly language, and from that, machine language. And as a computer scientist, that you know, no matter what program you write and no matter what really programming language you use, it all boils down to always to machine language, right? So, and you can think of the instructions of the machine language as like the axioms in some sense, right? So now what we're asking here is that is the same principles true for mathematical proofs? Can we take any proof and, you know, see that it boils down to, there's like a machine language of proofs in some sense, and it boils down to a set of agreed upon axioms. Right. So that's the first question, or the first problem with what is an obvious truth. But there's actually other important things here. Okay, so let's go back to Euclid. Okay, so here is Euclid's fifth axiom. This is the this is called the parallel postulate. Through a point not on a given straight line, at most one line can be drawn that never meets the given line. It's a weird way to phrase this, but basically what it says is the following. Okay, so you have some line. So, okay, so this is your line, and you're given some point not on that line. And then it says basically there is exactly one line that goes through that point that is parallel to your original line. And in fact, it is true on, you know, flat surfaces, but it turns out that it's actually not true on curved surfaces. Okay, so there's one illustration here on the right-hand side showing this, but actually, I think here's a better, nicer illustration. Using the parallel postulate, you can show that the angles of a triangle is 180 degrees, sums up to 180 degrees, but on a curved surface, this is no longer actually true. It can actually sum up to larger than 180, right? And this is actually now very interesting because it tells us that truth is really relative to your interpretation, right? So imagine like there's some aliens like living in a two-dimensional world, right? They live in the flat land, and that's all they know. That's all they have access to. It's flat land. So they come up with their own mathematics, and in their mathematics, in their axioms of mathematics, they have this parallel postulate, right? And it works fine. They never have any problems with it. It always works, and you know, that's great. But then you can have like three-dimensional creatures that look at the two-dimensional world, these other creatures, and they're like, no, we don't agree with your axioms of mathematics because this is not always true. Like we have three-dimensional space, there can be curved spaces, and so your actually axiom does not always hold. So this shows you that actually what you consider to be true can depend on your environment and your intuitions that are based on that environment, on that physical environment. So that's interesting, right? So then that questions you like, what is really true? Like, what do we mean when we say something is true? The other thing I think that this highlights, which is interesting, I think, is that it highlights our sort of limitations, right? Sort of like, you know, thinking about the flatland creatures, you know, we kind of discuss, you can see that as their limitation of their environment kind of limits their kind of mathematics, perhaps. I mean, you can take this to a more extreme and say, well, you know, suppose there are creatures that live only in one dimension, right? So they only know left and right, so they don't know any other dimension. So how are those creatures ever going to develop any kind of intuition or understanding about higher dimensions, like 2 or 3 dimensions? How can they ever judge the truth about higher dimensions? You know, that's interesting, right? So perhaps not, arguably not. And if you ask like about us humans, like what's like an obvious limitation to us, I would say it's the concept of infinity, actually. So our environment is finite, you know, our brains are sort of shaped by finite things. And when we start reasoning about infinity, that's where our, you know, intuitions and reasoning starts to break down. And there can be statements about infinity where it doesn't seem like we can judge the truth of it. Okay, so that's very interesting. Okay, so truth, the concept of truth, I just want to point out basically that it's trickier than you might think, right? So there's truth is relative to your interpretation. Which now brings me to the second problem, which is something that I started talking about now, is infinity. Okay, so as as our mathematical technology developed over time, we started, reasoning about infinity. We started reasoning about infinitely large things, transfinite numbers, and we also started reasoning about infinitely small things, like with calculus requires like these kinds of concepts. And people started to realize, there might be problems with these things, and with infinitely large, can we judge the truth of those kinds of things? With infinitely small, the definitions of infinitesimals was very problematic when calculus was, being used. Sort of, if you ask people to formalize what do you mean by infinitesimals, they didn't really have a good answer for that. And it seems like people were using like sort of circular definitions for infinitesimals. So it seemed like there were some concepts that were not well defined in mathematics that was being used in calculus. So that's a problem. Okay. And then there is Russell's paradox. I guess that, most of you have heard about it. I'm not going to state what it is right now. I'll say it later. But basically, for now, all I'll say is that Russell's paradox is an observation that if you use some naive definition of sets, and if you're not careful about how you define the notion of set, it can lead to actually inconsistencies, contradictions in mathematics, and can break mathematics. So you have to be careful about how you actually formally define the notion of a set. So that was like another thing that people realized that was problematic. And then finally, like the use of human language when we actually communicate mathematics and mathematical proofs, this is problematic. Because, let's say we use English, well, there are lots of ambiguities in human language. And if you write an argument for me in English, some kind of mathematical proof, well, it's possible that I may not really understand what you mean, what exactly what you're getting at. And these can be because of the use of human language. So what we would like ideally is a much more precise and unambiguous language that we can use to express our proofs. Okay, so these are the problems. What is the solution? Okay, so let's come back to this picture. So, right, we have the spectrum of mathematical reasoning. And what we would like to do now to fix these problems, so this is the Gorm territory, this red region. We want to extend this into a more formal territory, okay? So we want to make things, in some sense, we want to go to a more absolute formalism. Now, I don't like to use the word absolute. Nothing is really absolute, but, more absolute, right? Even more than what, professional mathematicians would use at the day and time, okay? And this region, I'm going to call form, okay? So form for formalism. So it's going to be Gorm versus form now, and we want to get to a more absolute formalism form. Okay, so we said like this is good old regular mathematics, something of interest, mathematical model, logic, and new knowledge, and so on. And form is now very interesting, okay, because basically the picture of form is you take the previous diagram, okay, and the thing now that we want to put under the microscope and understand better is mathematical reasoning itself, right? Gorm itself, right? So this is really the picture of form. We want to rigorously formalize and understand mathematical reasoning. So that's precisely what we want to put under the microscope and find a mathematical model for mathematical reasoning itself. So mathematical reasoning is what? I mean, you can say basically, this part here is mathematical reasoning, and you want to put this here, okay? And this makes form very interesting, but also quite confusing, quite mind-bending. because there's this meta nature to this whole process, right? So you're using you're analyzing mathematical reasoning with mathematical reasoning, and so it can actually get quite confusing. And the other thing is that, when mathematicians are doing mathematics, as I told you, like they live in the right-hand side here, right, in this world. They're not too concerned about the step of formalizing, like this step here, this arrow. But if you think about it, like arguably the most important step of form, or one of the most important steps of form, is precisely actually this modeling phase. So how do we go from mathematical reasoning GORM to a mathematical model of GORM? And now this raises very interesting questions, because now you're like, how do we model mathematical reasoning? How do we model truth? How do we model proofs, arguments, statements? And this will lead you to philosophical territory, of course, right? What is truth? What is a proof? And so on. And I mean, to be honest with you, to this day, people argue about these things, right? So like, there's not like 100% consensus, and people have different perspectives on these things. But yes, so this is tricky stuff, okay? But very interesting at the same time. So when you need to now formalize mathematical reasoning, GORM, you're trying to basically formalize the pieces, the elements of mathematical reasoning, which means like you need to answer the following questions, okay? So you need to answer, how do you formally represent statements that may be true or false? Which statements are going to be obviously true? What are the axioms going to be? And which deduction rules are going to be allowed? And how are you going to formally represent them? Okay, so these are the kind of questions that you have to ask and answer for formalizing mathematics. Now, a very interesting thing here that is hiding, a very important thing that is hiding, is the fact that mathematical reasoning, actually, if you think about what it is, it's actually computation. Okay, so if you think about human beings doing mathematics and figuring out proofs and communicating proofs with each other, really the thing that really matters in that process is really the fact that it's a information processing. It's a computation, right? And this is the key connection now between computer science and mathematics, right? That mathematical reasoning, on the one hand, is computation. And in fact, it's, in a certain sense, you can say there's an equivalence to these things, because mathematical reasoning is also general enough to capture computation. And mathematical reasoning is computation. So there's sort of an equivalence there. Okay, so there's a very interesting connection. But at the time, of course, people didn't even know. I mean, there was no concept of computation. People didn't know what that meant. The people didn't have a formalization of information processing. But, this is the quest to formalize GORM led to the formalization of computation inevitably. Okay, so now let me give you an overview, a very high overview of like the things that led to eventually form a successful formalization of mathematics. And I'm going to start actually very, very early. Start with Aristotle. And here I just want to give you a very big picture view. I'm going to skip through these things very quickly just to give you a sense of who the main players were. And then we're going to dive deeper later in the course into some of these aspects. But now I'll tell you some of the main players in chronological order by birth. And the first person I think, that we should mention, we should talk about is Aristotle, who is an amazing philosopher, one of maybe the top philosopher of all time. And the description that I gave you for mathematical reasoning and proofs is exactly was his idea of logic, right? He said logic and reasoning is about having unambiguous statements. It's about having some precise deduction rules, some deductive reasoning. And also you have to have some kind of a first principles approach. So he realized that, you have to start with some base set of axioms, because otherwise you're going to get infinite regress, and that's not good. That won't work. So you do have to start with some base set of axioms and then build things up. And this is exactly what I described to you in the beginning of the lecture. And this was actually all the way back, it goes all the way back to Aristotle. Okay. And the incarnation, the mathematical incarnation of Aristotelian logic is the Euclid's elements, right? So really, when you look at Euclid's element, as I said, Euclidean geometry, the 5 axioms, deriving everything systematically from the 5 axioms is really, materializing Aristotle's vision of logic in a very, very concrete way, which, as I said, set the standard for future of what a math proof should be like. Then I'm going to go all the way to Leibniz now, 1646. He had a very interesting, idea for logic. He envisioned an algebra calculus of logic, which was kind of like a mechanical view of logic. So call it like a computational propositional logic. And he thought that, logic should be sort of basically like calculation, right? Very mechanical, like calculation. And he thought that, if two people ever had a disagreement, there should be a way to just calculate who is right and who is wrong, right? So that's the kind of vision that he had for logic. So his famous quote is, "Let us calculate without further ado to see who is right." Okay. Now his work or his ideas really remained at the concept level, nothing very concrete. So someone who made things a concrete step towards this vision was George Boole, 1815, the inventor of propositional calculus. And you probably know propositional calculus, like you have variables with truth value, like you can have x and y or z, and you have Boolean connectors, you have and, or, and not, and you can have expressions like these. And this was a very good step. Indeed, this is like the foundation of, first order logic with quantifiers, but this was not enough, right? In some sense, even though it was a good first step for sure, we need a richer language to describe statements and human reasoning. Now, another important person here is Cantor, born in 1845. This is the man who is considered the father of set theory and the person who dared to tackle infinity head-on, okay? And he's considered the father of set theory because it's not like there wasn't set theory before Cantor, but set theory with finite sets is kind of, trivial, nothing too interesting there. And set theory becomes interesting when you now start thinking about infinite sets. And now when you start thinking about infinite sets, this is like Cantor's work, I think, is one of the things that really one of the things that accelerated the need to formalize mathematics, because many of the mathematicians at the time completely rejected Cantor's work. Like they were like, nope, we don't accept this as proper mathematics. This is not good mathematics. On the other hand, there were other mathematicians like Hilbert who completely embraced Cantor's work. So now you have like very famous mathematicians on one side who say like, this is not proper math. Then you have other very famous mathematicians saying, this is absolutely proper math. And so you have a big disagreement. So that shows like, okay, we need a better understanding of what's acceptable and not acceptable. So, Cantor's work is important in various ways, but in one way, this was important. And then we come to Frege, 1848, and now he's taking the next step after Boole, laying the foundations for first-order logic, predicate calculus. And first-order logic basically is a framework that allows you to basically formalize any area of mathematics. Like you can precisely represent statements in any area of mathematics you want using the language of first-order logic. He proposes axioms for set theory as basically the foundation of all of mathematics. Why set theory? Because people started to realize when people were working on this that set theory or sets seem to be at the foundation of everything. They realized that you can define numbers using sets and that you can define functions using sets, and then you can define, tuples using sets and sequences using sets. And it became clear that you can build up any kind of mathematical structure, you can build it up from sets. So this is why set theory is important, and this is why Frege worked on axioms of set theory. He worked for a very long time, 10 years, writing 2 thick books about the system. And then came Bertrand Russell, big fan of Frege and really liked his work, and wrote to him and said, look, this is really great work. On the other hand, he says, I observed something about your axioms. He said, your axioms allow me to define the set of all sets that do not contain themselves. So in set notation, he says, your foundation of set theory allows me to define this set D, which is the set of all those x's, such that x does not contain itself. But then he says, consider the question of whether now, okay, so first of all, let me say this. So then, notice that, so for any set y is in D if and only if y is not contained in itself, right? So this is the definition of the set D. But now if you replace y with D, right, setting y equals D, you get D is in D if and only if D is not in D. Contradiction, right? So then this is inconsistency, boom, your axioms really don't work. How did Frege respond to this? Well, he was not very happy, of course. I mean, imagine you if you were spending, this was his life's work, okay? This was his life's work, and he was, not a good situation to be in. On the other hand, here is a direct quote by Russell about Frege. He said, and I'll read this to you, "As I think about acts of integrity and grace, I realize that there's nothing in my knowledge to compare to Frege's dedication to truth. His entire life's work was on the verge of completion. Much of his work had been ignored to the benefit of men infinitely less capable. His second volume was about to be published, and upon finding that his fundamental assumption was in error, he responded with intellectual pleasure, clearly submerging any feelings of disappointment. It was almost superhuman and a telling indication of that of which men are capable if their dedication is to creative work and knowledge instead of cruder efforts to dominate and be known." Okay, so Russell was very impressed by Frege, although this did affect Frege's mental health quite a bit. So I don't know, maybe he was kind to Russell, but internally I don't know what was going on. But in any case, I think this is a very nice quote because it actually highlights one of the reasons why I love mathematics, and one of the things that really attracted me to mathematics was precisely this, that in math, it's not your opinion against my opinion, right? So, if you argue something and it's true, it's true. There's some level of, objectivity here that you cannot escape. And that was very attractive to me. And I think, this is sort of what Russell is referring to here as well. Okay, so now this brings us to Russell. He then took on the task of actually putting mathematics on a solid foundation. He didn't work by himself. He worked with Whitehead, and they worked for many years, 10, 15, 20 years, and they eventually published Principia Mathematica, and in volume 2 of Principia Mathematica, page 86 of volume 2, they managed to prove 1 + 1 = 2, and they said the above proposition is occasionally useful. So I had a good sense of humor about this. So you see, this was an extremely tedious task. Writing a proof like this is really analogous to writing a computer program in machine language, right? So even a very simple statement, in, let's say, a simple instruction in Python could translate into, thousands of instructions in machine language. And this is really what was going on. Russell was not really happy with the work, I should say. He was never like really 100% satisfied with their approach. But Whitehead was like, dude, come on, we have to publish something. This has been going on for like decades now. And so he convinced Russell to publish, and then they published. And it has served an important purpose. I think like after this work, people were convinced that, so we can put mathematical reasoning on a solid foundation. So they didn't go all the way. I mean, at some point you give up, of course. Like you cannot just derive all of mathematics like this. They did give up at some point, but I think they did just enough to convince people that, yes, I mean, this can be done. Now, another important person is Hilbert, David Hilbert. And I should say, of course, I'm going chronologically by birth date, but, a lot of things are now happening simultaneously in parallel, of course. And David Hilbert was a very important figure, in the quest to formalize mathematics. He really, maybe in some sense, you can say, popularized also this effort to formalize mathematics. This is actually known as Hilbert's program. So Hilbert's program, you can say, has the following pieces. Hilbert's program asks for a precise formal language manipulated according to well-defined rules. And there's this thing called Hilbert's system, which is first-order logic plus a set of deduction rules. Okay, and even though this is called the Hilbert system, it's really, should be given credit to both Frege and Hilbert, because Frege did important work in terms of first order logic. But so this kind of formalization package of, first order logic plus the deduction rules gives you the Hilbert system, which allows you to now formally represent statements, formally represent deduction rules, which means now you can formally represent, arguments. And so that was an important piece. He asked for a formalization of mathematics that was complete and consistent, which meant basically that for all statements S, either S or the negation S should be provable in your formalization system. And he was very optimistic about this. Like he really thought that it would be possible to get a complete and consistent formalization of mathematics. And he has a famous quote. He said, "For us, there is no ignorabimus, and in my opinion, none whatever in natural science. In opposition to the foolish ignorabimus, our slogan shall be, we must know, we will know." So his thought was like, whatever we need to know, we will know, okay, or we can know. In principle, he thought that everything in principle is knowable and provable. And then the other thing we talked about is Entscheidungsproblem. He also asked for an algorithm for determining the truth of any mathematical statement as well. And of course now, like slowly this notion of computation is like slowly starting to emerge to the surface. And Kurt Gödel actually is realizing, he's of course a very important figure as well. And, he's working on these things and he's realizing that, Hilbert is optimistic, all right, but he doesn't think this is going to be possible. But, he has two very important theorems. The one, maybe the less known one, but I think maybe in some sense the more interesting or the more impressive one, in my opinion, perhaps, is the completeness theorem. Like people know Gödel for incompleteness theorem, but he has a completeness theorem. And he basically, completeness theorem says that any statement that is a logical consequence of the axioms in the Hilbert system can be deduced, proved in the Hilbert system. Okay, so in some sense, he's saying like the Hilbert system is a complete system, is a good way to formalize mathematical reasoning, and so like you're not going to be if you're not able to prove something, it's not going to be because you didn't have enough deduction rules. So what completeness theorem is saying is that Hilbert system is a complete system in the sense that if this thing is a logical consequence of these statements, then you can derive in the Hilbert system, can go and there's like a way to deduce that in my formalization, in the Hilbert system formalization of mathematics. So, and then there's the incompleteness theorems, right? So the incompleteness theorem says, so in some sense, let me go disappear. So I think one nice way to interpret completeness theorem is to say that your Hilbert system formalization has enough deduction rules. You're not, if you are suffering from incompleteness, meaning that if there are some truths that you're not able to prove, the completeness theorem says that this is not because you didn't put enough deduction rules, but you can suffer incompleteness another way. Maybe you didn't have enough axioms, right? So maybe there's some statement, true statement, and you're not able to derive it, and that might be because you don't have enough axioms. And what incompleteness theorem says is that because we have completeness theorem, so like we have enough deduction rules, and incompleteness theorem says that actually you'll always suffer from incompleteness, meaning that no matter what axioms you choose, of course there has to be some reasonables to the axioms, because you cannot say like my set of axioms is the set of all true statements, and that defeats the purpose. But for any reasonable set of axioms, and there's a precise notion for what that means, there's always going to be some true statements that cannot be proven. Okay, so there's always going to be statements that are not going to be logical consequence, true statements that are not a logical consequence of your axioms. And that was a shock, right? Like, this was, I'm sure it was a shock for Hilbert, but also for many other mathematicians at the time. And we're going to talk about Gödel's incompleteness theorems. I'm actually hopefully going to prove that to you. But then, to finish off here, so Alan Turing from 1912, father of computer science, of course, he, like Gödel, actually realized that we need to define this notion of computation. He never really got a convincing or a satisfactory definition of computation. But nevertheless, he marched on and, proved the theorems that he proved. But later, Alan Turing gave a very satisfactory definition of computation and algorithm. And he also showed that there's no algorithm for the Entscheidungs problem. And if you are interested in this stuff, I definitely recommend this comic book, Logicomics, that sort of follows Bertrand Russell in this story of the foundations of mathematics, and it's very interesting. Okay, so the upshot here of all of this is that you can rigorously formalize mathematical proofs, right? So especially the work of Russell and Whitehead really convinced people. And, the Hilbert system is a good formal system. We do have satisfactory axioms for set theory, like the modern one that people would agree on as like the ZFC CFC axioms for set theory. So you can rigorously formalize mathematical proofs. We also know now that there are limits to what can be proved. There are actually truths that are in some sense not attainable, right? We cannot prove it, so we don't know. Computer science, as a result of this, is born. The computing revolution begins. And computers, once you have computers now, it's interesting because it elevates the significance of formal proofs. Now, as I told you, okay, we could formalize mathematical proofs, but no one wants to work with formal proofs. It's like by hand, right? It's kind of ridiculous. But now that we have computers, it actually makes us revisit and say, oh, wait a minute, formalizing mathematics, we can actually handle this now with computers, right? It's not so bad anymore. Okay, so, and we're gonna say more about this, but let me give you one last story in the spirit of, formalizing mathematics. So this is a story about Lord Vacker van Wankenfels. That's the name. Actually, this is not a picture even of him. It's like, I think I just Googled some random 16th century dude, and this is what came up. And this is even not a story about him. This is about Kepler's conjecture. So Kepler, 1611, as a New Year's present for his patron, Lord Vacker van Wankenfels, wrote a paper with the following conjecture. He said the densest way to pack oranges is like as follows, right? Or it wasn't about oranges, it's about spheres. So this is the way to pack spheres, he said. Now this all, I'm not being precise here, but you kind of get the point of the statement. This remained a very important open problem for centuries. Until 2005, Pittsburgh native from University of Pittsburgh, Tom Hales, submits a 120-page proof in the top mathematical journal in the world, Annals of Math. Plus, he submits code to solve 100,000 optimization problems. That takes about 2,000 hours of compute time. Now, normally when you submit a paper to a math journal, you might get 2 or 3 referees who will read your paper very carefully and then, first of all, verify that it's correct and then also give you feedback and then make the determination in some sense whether the paper will be accepted or not. Now, this was such a huge task, such a big problem. This is Kepler's conjecture, such an important conjecture that, Annals recruited a team of 20 referees for this, 20. So they started working. They worked for 4 years. Some quit along the way. Some retired. And actually one died, unfortunately, in the process. And at the end, they kind of gave up. They were like, okay, we're 99% sure it's a good proof, but, we can't say we're 100% sure. So then Hales was like, no, I don't accept this. I will actually code up completely formal axiomatic deductive proof that will be checkable by a computer program. And he started the project FlySpec, open source project. Took 10 years with 21 collaborators. They published a formal proof of the Kepler conjecture. So formal proofs are now actually a thing. Yeah, and now, once you have a formal proof, which is checkable by a computer, it's done. It's game over. This is like the gold standard for what a proof is and for correctness of a proof. It's definitely, you can definitely, the only thing that you have to sort of trust, if you will, would be the 400 lines of code that checks the deduction rules and just applies the deduction rules one by one to check that it follows correctly. But these deduction rules are syntax rules. These are string manipulation operations, right? You can write various different programs to do the same thing. If you don't believe that particular proof checker is not correct, you can run another proof checker and see that it's going to be correct. So, once you have a proof like this, it's proven, right? It's much more solid than any human proof for sure. Okay, so we have proof assistant softwares now like these. They do a couple of things that check that a formal axiomatic deductive proof is a valid proof and help users code up such proofs as well. And in fact, in some situations, they can find proofs that people have not found before. This is a good example. There's a Robbins conjecture which was open for 63 years. It doesn't matter what this means. Don't worry about it. All Robbins algebras are Boolean algebras. Some conjecture that was open for 60 plus years. And this was proven by an automated theorem prover, EQP. Kind of like did a brute force search to find the proof, to be honest. Yeah. And here are some formally proved theorems now. Gödel's incompleteness theorem, four-color theorem. So now four-color theorem is really like on a solid ground, Kepler conjecture, and so on. Okay, so now what does this all mean for 251? And sorry, I'm going over time a little bit, but I'm almost done. Okay, so so we have the Gorm territory, and we talked about form, absolute formalism, which is possible, which is great. Now, of course, it would be ridiculous if we expected you to write proofs which are like can be formally verified. It would be great for the TAs, would love it, right? So then we don't have to read the proofs and verify ourselves. The program could check it. But, maybe that, in some sense, that might be the future. We'll talk about that. But for now, we don't expect that. So we're going to be expecting more like, here, this territory, which is kind of like, closer to how mathematical, professional mathematicians would communicate proofs. But, a proof basically in our course means the following, okay? It's an argument using precise definitions and logical reasoning that convinces the reader that the assumptions lead to the desired conclusion, basically. And what I want to emphasize here is that it has to convince the reader. And in that sense, a proof really is sort of, what is an acceptable proof is really a social construct, if you think about it. But I think, this part, convincing the reader is very important. And you have to choose the right reader in some sense. Now, it's very natural for you to be confused at some points about like whether you're giving enough detail or not, okay? And that's very natural, You may not know sometimes whether you are giving enough detail. And that's natural also because you see like there's always room to be more formal. Unless you're writing your proofs in complete formalism, checkable by a computer, there's always more room to be formal. And unfortunately, I won't be able to tell you, I won't be able to give you a precise description of like this level of detail is enough detail. So there's no description like that, unfortunately. The best thing I can do is I can give you this kind of a description, which I'm giving you here, and then tell you that when you write your proofs, the audience that you should have in mind, the reader you should have in mind, is another classmate who has not thought about the problem before, who has not, does not have the intuitions that you might have developed by when you thought about the problem deeply. So you have to keep your audience in mind and write your proofs in a way such that the audience, when they read it from start to finish, they will be convinced that this is a correct argument for the statement. Okay. So that's it, guys. So form and computation, once again, I'll highlight the fact that, in all of this, the connection with computer science is that, mathematical reasoning itself is computation. And we're going to talk about more mathematical reasoning and Gödel's incompleteness theorems. But of course, what we need to do first is formalize computation. Let's understand what computation is. Let's prove some basic properties about computation, and then we'll see how those basic properties of our computation will lead to interesting results about mathematical reasoning and in particular the incompleteness theorems. But this is more on this later.